Thanks very much for giving me this opportunity, and I will straight away start with where Raghu finished, I think, and Shambi introduced some of these things yesterday. So I will talk about observing this 21 centimeter signal from the epoch of reionization using one of the very powerful telescope, the Murchison-Whitefield array. So let me begin with this statement that we are in an exciting time where we are detecting the 21 centimeter signal in the post-EoR region. The telescopes such as CHIME, Meerkat, which has already detected the signal with very high significance, either directly or with cross correlation with galaxies. And as Raghu shared, that we are in a time where we are making very deep upper limits, where we can start ruling out models of epoch of the reionization. And we are now improving on those things. So my talk will be on how we process the data, how we remove the foregrounds, how we deal with some of the systematics, particularly focusing on this telescope, the Murchison-Whitefield array, which is a precursor to SKA, and very similar things is expected to happen with the SKA array. So this is a plot of the bandpass of the MWA telescope. So this is a frequency axis, and this is the response of the telescope at different frequencies. And you can see this peculiar structure in the bandpass, which comes because you cannot correlate so many antennas at the same time with very high resolution and frequency. So you have to have some kind of you cannot sample the signal at a very high resolution for the entire antenna, for all the antenna, and you end up having this kind of features in the bandpass. And this is the actual data that we measure from where we want to measure the 21 centimeter signal. So the x-axis shows the frequency, and y-axis arbitrarily shows the measured visibilities, amplitude of the visibilities. So the measurements are called visibilities. What we measure in interferometer is called the visibilities. And you can see these gaps every 1.2, after every 1.28 megahertz there is a gap which comes from the bandpass of the MWA. This is from actual observation carried out using the telescope, and the data has been described in this paper. What happens when you do estimate and power spectrum from this data is this. So this is K perpendicular, it tells you about the angular scale, and this is K parallel, this tells you about the frequency or the line of sight in this case. So you see the lower K parallel regions are dominated by foregrounds. These are very strong signals, and these signals is repeated in the higher K parallel. So typically what we expect is that the foreground will be limited to this region, some wedge region, and this region will be free for you to do your studies, but this is not the case when you have such kind of bad band passing. So how do you deal with that? So there are these regions from where you can measure the power spectrum, put upper limits, but then you have these contaminants, and then your limits are not good enough. And this is the same pattern you will see in all the MWA power spectrum papers that is there in the literature. What we do, we take an alternative approach. We do not take a direct Fourier transform of the visibilities along the frequency. Rather, we measure this quantity CL delta nu, which is the 2-point correlation along frequency plus the assumption that the signal is ergodic along frequency. So what matters is the separation between the two frequency, not the individual frequency. So you can first do a 2-point correlation and then do a Fourier transform to get the power spectrum. And it is shown in the simulations that even with flagging and no flagging, so these are the same flagging as the MWA data has, but you cannot distinguish with you can recover the signal in this method, and there is no such abrupt features in the power spectrum. So simulation shows that this works, and this is the result from the actual data. And I will come to this plot again and again, and you can compare that in this plot, which directly Fourier transform the visibilities along frequency. You will see this kind of reoccurring foregrounds at higher K parallel. This is not the case here. But if you look at very carefully, this is also not quite free from the foregrounds. These are at least 3 to 4 orders of magnitude smaller than the highest value, which is improvement, but then there are these ripples. The problem with this is that if you integrate over time, these ripples will not go away. The noise will go down, but these ripples will stay. So you have to figure out some way to mitigate those ripples. So this is the problem that is the main focus of this work. And so we investigated why these ripples are coming. Even so, our idea is that in this kind of estimator where you estimate CL delta nu, we shouldn't see the ripples, but still you find these ripples. And we finally found out that, I will not go into those very details because that will not be very much interesting to all of you. But what turns out that this assumption that the signal is ergodic holds to some extent for the 21 centimeter signal, but it doesn't hold for the foregrounds. And so this kind of ripples appears when you have a data, when you use data that have foregrounds, but doesn't appear when you have signal. So what do you do? So this is first. The first thing is that we understood this, where this problem is coming from, and then this is an explanation of the same thing, that an ergodic signal. This is the frequency axis, and this is the frequency separation axis. So an ergodic signal looks very similar along the frequency axis, which is not the case here because the data is foreground dominated, and there are other structures in the data due to the instrument. But this is the problem, that we are averaging over this direction, assuming that the signal is ergodic, but because the signal has mostly dominated by foreground, this assumption doesn't hold, and those tiny ripples comes up in your final power spectrum. So we proposed a new method to deal with this. The idea is that if you can remove the foregrounds, or at least the amplitude, you can reduce the amplitude of the foregrounds, and you can reduce the spectral behavior of the foreground to some extent, then you can mitigate those ripples. So let's see if that happens in the case of real data or not. So what we did is that we tried to find out the smooth part of the data. So we did some kind of windowing using a hand window. There are many other methods. We found that this works very well. So we use this hand window to find the smooth part of the data, and then subtracted the smooth part. And I will show that there will be no signal loss beyond the smoothing scale, and anything that is less than the smoothing scale, we will not use that. So this will be a hybrid approach where you will remove some of the foregrounds and then avoid those regions to constrain your signal. So this is what the values will look like. The signal now will look like mostly ergodic, and then now we are in a position to average this signal to get a power spectrum which we expect to be like this, and this is what we get from the actual data. So this is the main plot that the main result of our work. This one is before the smooth component filtering. You see that as I said, that the power is much lower than the lower k parallel values, but now we can see this is much more cleaner, and we are now in a position to check whether this is consistent with noise or not, or can we constrain the 21 centimeter signal using it. This region is excluded in our analysis because we have filtered the smooth part of the data, so this region doesn't concern us. We are not using this region. This is the same method. So one of the questions that we have been asked for many times, that did we try our methods on simulated data and run it through the whole pipeline? Yes, we do. We do it routinely. So this is a 21 centimeter simulated 21 centimeter signal that goes through the entire pipeline, that is making the visibilities, running foreground removal, filtering out the smooth part, and you can see that in this region this is very similar before and after the smooth component filtering. If you estimate the power spectrum, you will see that beyond the smoothing scale, this matches very well with the input EoR model. So our method works. This is the final result. This is the power spectra, the spherically average power spectra that we get before this smooth component filtering, and after filtering out the smooth part, we are very much consistent with the noise, and this is a very around 2 orders of magnitude improvement from without this SCF method. We didn't stop there. We tried to see if these values are actually consistent with noise. So we compared it with noise simulations and found that this is very much very much consistent with noise. There are some excess variance of a factor of around 1.4, but this is very negligible if you compare with before SCF thing, and this is consistent with the statistical fluctuation within 2 sigma. So all the analysis has been shown with only one pointing center. So I didn't describe about what the data, what the observations are. So now I will come to that. So this was a drift scan observation where the telescope is sitting at one place, the sky drifts over the over it, and we have only analyzed only one pointing center. From that we have got a very deep upper limit. Now we have 163 of such observations, and Shovik has done this huge task of analyzing power spectrum for all the pointing centers, and he has found upper limits on all the values for all the entire RA range that can be probed by the MWA. So one thing we can see is that the power is very much, the upper limits are very well constrained in these regions, but not in these regions, and that is mostly because of this 4NAX-A source that comes into the side lobes of the MWA telescope, and also the diffused emission that comes into the side lobe of the telescope. So we decided to only focus on these regions. We wanted to combine the power spectra from these regions, and we found this combined power spectra after this smooth component filtering, and found this kind of pretty much Gaussian-like behavior of the noise statistics. So we are very much confident that this is consistent with noise. And in the upper limits, so these are the upper limits with only one pointing center, that is 17 minutes of data, and with the entire drift scan observation, 6.2 hours of data, we got an upper limit of this. And you can compare with the approach where one directly does a Fourier transform along the frequency. The upper limits are the upper limits from 110 hours are very similar to the upper limits that we got from 17 minutes. But the problem is that because we are filtering out some of the smooth part of the data, we are not able to probe the low K value. So this is some of the drawbacks of these methods, that you cannot access the largest scales. But this is still very much improvement than a traditional method of directly Fourier transforming. That is all from that. We now need more data points to add and go down in the upper limit. Next, I will show some preliminary results from the same data. Using the same data, we want to measure the EoR. Can we measure the EoR bispectrum? This work is led by the PhD student Sukhdeep, and this is the formalism is very similar. Instead of doing a 2-point correlation, you are doing a 3-point correlation now to get the angular bispectrum. And I will show some results from some specific triangle configurations. These are very preliminary results. We got report yesterday actually, and they are very promising. And these are some of the measured multi-frequency angular bispectrum. And these are, since the data is foreground dominated, the bispectra is the bispectra of the foregrounds, not the signal. And there are some, we see that for different triangles, the foregrounds, the correlation of the foregrounds are slightly different, but we are not, I mean, we are just presenting the results. We don't know the actual interpretation of what is happening there. And this is the bispectrum. So once we do get the multi-frequency angular bispectrum, we can do a 2D Fourier transform to get the EoR bispectrum. And one question that comes is that where is the wedge? So the wedge is a little bit complicated here. So in this axis I am showing the K2 parallel. So now right now in power spectrum we had only K perpendicular and K parallel. We now have K1, K2 perpendicular and parallel, and 3 K perpendicular, and it is difficult to show it. But this K2 parallel is shown here and K1 parallel is here. And the EoR window are somewhere in these regions, and it depends on what kind of triangle you are measuring and what kind of triangle shapes you are considering. But if you show it in a slightly different way, this looks very similar to power spectral results. And more details we can discuss later. And we have used this to put upper limits on the 21 centimeter bispectrum. This is one of the first studies to get upper limits on the 21 centimeter bispectrum. These are pretty high than the expected 21 centimeter signal, but these are very preliminary. So I hope Raghu will at some point we use this upper limit to put more tighter constant on the IGM parameters. And this has been done for all the triangle shapes. So this is a summary. Don't do a direct Fourier transform. Estimate the maps, then do a Fourier transform. That's the first message. The second is that even if you do that, you will see very tiny ripples, and you should do some method to filter out the foregrounds, which we call the SCF, but we seek better methods for this. And we have put very tight constraints from only 70 minutes of data, and we are in the process of improving it. I have shown some preliminary results which shows very deep upper limits, and we have put first upper limits on the 2170 bispectrum. So that's all.
Okay, thank you. Questions?
You showed a power spectrum curve with SCF. So in that plot, what explains the reduction in the error bar at high K?
Right, this one, right?
Yes.
Yeah, so the error bars in the measured CL delta nu or the maps depends on the amplitude. Since we have removed the smooth part, the amplitude part of the data, so the error bars also decreases.
But
So if
that
you
is the low K part, right?
yeah, it depends on the overall amplitude.
Yeah. So as if this wedge you talked about in the bispectrum, is this the theoretical wedge you're talking about, or whatever you see from the data? By theoretical wedge, I mean this
Yeah.
horizon limit, what you do for.
Yeah, so this is the theoretical line.
So this is obtained from that whatever visibility formula.
Yeah, so there is a formula that it depends on, there is a, so this is linear, so there is a direct formula from K, between K perpendicular and K parallel from where you get this horizon line. So it depends, so it is the horizon of the telescope, that's it. So this is the theoretical line and this is the wedge that you get.